A very good day to all. Now I'm going to demonstrate to you how to solve one of the example 4.5, using the red flag model for a distillation process. So I will skip the properties tab. So you have to make sure you include the components, you include the suitable property method, and generate the properties for all the components involved in this process to ensure the results are available under the properties tab. So the components involved here is N-butane and cis-2-butene. Okay. So let's shift to simulation tab. So under the simulation tab, we have to first construct the flow sheet. So we go to column, so just choose red flag. So you have to connect the block with the stream. So here you have to connect to total condenser, meaning liquid distillate. Okay, liquid distillate. Here, okay, you have to bear this in mind. When you have liquid distillate, you have to connect your distillate stream with this option. Okay, and you have the bottom stream. So you can change the block name, T101. You can also realign the whole diagram by pressing Ctrl B after you select the whole diagram. Okay, now if you try to minimize this for economic analysis, minimize this, and then if you don't know which page to go, you can actually click next, as I mentioned to you before. Click next. Then you'll be guided to a page for you to put in the feed information. Okay, so in the question you are given Weber fraction and pressure. So pressure is 1 bar, Weber fraction is I think 0.5, and the molar flow rate for each component is 50 kilomole per hour each. So if you have put in your right section here, composition, in terms of mole flow, you don't really need to put in the total flow rate here. Okay, unless on your right you have actually put in mole fraction, then you need to put in the what they call the total flow rate here. Okay, next would be the place for you to put in the column information. First page here would be the configuration. Okay, it is under T101. Under setup, you have this configuration. So we use equilibrium approach. Okay, this is not a rate-based approach. This is equilibrium approach, a typical one. Okay, so the number of stages is 83 if you check from the simulation results of the STWU, and the condenser here is total condenser. So the rest, the boiler type is kettle. The valid phase is vapor liquid. Of course, we are having distillation column. The valid phase must be vapor liquid, and we are going to use the standard method as the convergence method. So by default, it is actually the distillate rate and reflux ratio as the operating parameters. But from the STW simulation result, rather than getting distillate rate, you get actually distillate to feed ratio. So you can choose distillate to feed ratio here. Of course, if you know the distillate to feed ratio and the feed molar flow rate, you can also calculate the distillate rate. It's up to you. You can calculate the distillate rate separately using this info, or you can choose this info directly, distillate to feed ratio. So it is actually 0.5 based on the simulation results of the STWU, and the reflux ratio is, let me check, reflux ratio is 26.18. So 26.18 is the reflux ratio. So we are done. You see the blue tick here. We are done for the page of configuration. Let's shift to the next page. So this is the page for you to put in the stream information. So of course, feed stream, again, you can get it from the simulation result of the SCW. It is 46. Okay, so you only need to put in the feed stage. The other two, like where is your distillate stream and where is your bottom stream, you actually use the info that you have put in by default, because stage 1 by default is the condenser stage, and the last stage, stage 83, is for your reboiler. Okay, so next would be the pressure tab. Okay, here you need to put in, typically I will just put in the condenser pressure 1 bar, and assuming there's no pressure drop across the column. If you know the pressure drop, you can actually include the pressure drop details. Okay, if you look at here, pressure drop details in the third section is actually an optional. If you know, then you can put it. Okay, so let's proceed by clicking next. Okay, now you have all information required and you are asked to run the simulation. Okay, run the simulation, and in order to get the answer for question A, you have to check the stream result to get the N-butane composition in the distillate. Okay, let's go to the block, the stream result here. Okay. Before you harvest the result, make sure this status is there, results available. If not, then you have to troubleshoot what are the problems encountered. Okay. Mole fraction, so N-butane. Okay. N-butane, so this is the mole fraction of N-butane, 0.9858, meaning the N-butane mole purity in the distillate is 98.54 mole percent. So this is the answer for question A. Okay. Let's proceed further. I think we have to set up the design spec so that we can achieve the mole percent of N-butane in the distillate of 99%. So it is a little bit more we need to adjust. And we have to manipulate the operating parameters so that we can achieve 99%. At the moment, we only get 98.58%. This is not meeting the target. So we go to the design spec of the column. So look at here on your left. So you have design and design spec and vary. Okay. Design spec, you click new. Okay. What you need to do is you can put the description, or you can even skip the description, no problem. I put butane more purity in the. So in order to answer question B, you have to use the design spec vary function in order to achieve the 99% of N-butane in the distillate. So first you have to create a new design spec. So the description, you can put it as butane more purity in